In waves and oscillations, till now we have discussed 3 chapters in very detail. In first chapter, we have discussed the free oscillations of systems with 1 degree of freedom. When you say free oscillations, what does it mean? You have seen that the oscillations under only the restoring force with no damping, that is oscillations in a resistance-less medium, is called free oscillations. Actually, a system is said to have 1 degree of freedom if it is completely specified by a single quantity or variable. So our discussion in case of free oscillations was limited to the problem of with 1 degree of freedom. And you have seen the various important examples of such free oscillations. Okay? I have just given you a review what you have learned in the previous lectures in waves and oscillations, because today we are going to discuss a new type of problem which is called coupled oscillations. So first of all, in this lecture we will only see a brief introduction regarding these coupled oscillations. What is the basic difference when you talk about the coupled oscillations and the free oscillations and forced oscillations? So our aim is only to introduce you what do you mean by coupled oscillations, and after that we will actually start our real chapter, real concept, when you will learn several things and several new concepts. Okay? As I have told you that first of all we have learnt about free oscillations with 1 degree of freedom, and just for a review I am giving you 3 important examples of these free oscillations. So in first example, let us consider there is a simple pendulum, and this pendulum is oscillating in a medium which is resistanceless, or it is vibrating in free space. In this condition, you know, only the force of gravity provides the necessary restoring force for oscillations, and there is no damping force acting on the bob of the pendulum. Actually, this is an ideal situation. In practice, such a free oscillation is practically impossible. In case of the oscillation of a simple pendulum, you know, the only quantity which is needed to describe the motion is this angle theta, which the string of the pendulum makes with the vertical at any moment t. So in terms of this variable theta, we can completely specify the motion of a simple pendulum. And so as only one variable theta is needed to describe the motion of a simple pendulum, so that we simply say that this motion or this oscillation has 1 degree of freedom. Okay. Similarly, you have also learnt about the spring mass system. This is another very important example of free oscillations with 1 degree of freedom. In a spring mass system, you know, there is an ideal spring with a spring constant K, and one of the ends of this spring is attached to a wall. As you can see, this is the point A, where one of the ends of the spring is attached to a wall, and the another end is connected to a block of mass m, as you can see in this figure. Actually, this mass is placed on a horizontal surface, and if the spring is neither stretched nor compressed, that is, the spring is in its natural length, then net force on this block is 0, and you simply say that our system is in equilibrium. But when we displace the block from its equilibrium position, let us say by x, x is the displacement by which this block has been displaced from its equilibrium position, and it is released, then you know that this block executes simple harmonic motion about its equilibrium position, let us say O. Okay. So this displacement x from the equilibrium position of the system is the variable in terms of which you can completely specify, completely describe the motion of this spring mass system. And so that we need only one variable x, which represents the displacement of the mass m from its equilibrium position, for discussing the motion of this spring mass system. And since only one variable is needed, so we simply say that this oscillation is also with 1 degree of freedom. Okay, I think you are getting the things. All these things we have learned earlier. I am just giving you just a revision, because our aim is to deal with the problem of coupled oscillations. So before knowing about coupled oscillations, it is very essential to know what is the basic difference between the coupled oscillations and the free oscillations, okay, and other concepts which we have learned earlier. The third very important example of free oscillation with 1 degree of freedom is an electrical circuit which is called LC circuit. As you can see in this electrical circuit, this L is an inductor and this C is a capacitor, and both are connected to one another. If the capacitor is charged and the circuit is switched on, it gets discharged. And if you want to deal with this circuit, the electrical nature of this circuit, you see that the charge Q on the capacitor oscillates simple harmonically, or the current I through the inductor also oscillates simple harmonically. Okay. So if your aim is to deal with the problem of this LC circuit, this can be completely described either in terms of charge Q on the capacitor or the current I in the inductor. So again we need only one quantity, which is either the charge Q or the current I, for discussing the behavior of this circuit. And so we simply say that this is also a problem of free oscillation with 1 degree of freedom. Actually, the basic feature of free oscillation with 1 degree of freedom is what? This is actually that this oscillation has only one single frequency, or you can say that this oscillatory system can be characterized by a single natural frequency. So mark it, when the degree of freedom will be 1, then our system can be characterized by only one frequency. There is not a group of frequencies, but there will be only one unique frequency. Okay. So this is just a prerequisite important revision for you about the free oscillation. Okay. And I think you have got all the facts which we have learned earlier in very nutshell. Okay. After dealing with the problem of free oscillation with 1 degree of freedom, you have learned about the problem of forced harmonic oscillation, okay, in very detail. Actually, in case of the forced harmonic oscillation, you know that the oscillation of such systems is characterized by a single frequency. Again, this is also a problem of oscillation with 1 degree of freedom. But in this case, we have seen that there is a there is a source of energy which is connected to the system which have to oscillate. Okay, as you can see in this figure, this I have marked here a word driver, and this driver means this is source of energy which is coupled to the driven system, that is the oscillator. When you say driven system, that means oscillator, and this driver means source of energy, and both are coupled. Okay, actually in this case there is a loss of energy of the driven system due to the damping, you have learned, and that lost energy is maintained, compensated by this driver. It means this driver provides the harmonic force, or provides the energy which maintains the energy of the driven system, and our oscillator just oscillates like a free oscillator even after loss of energy, because that loss of energy is compensated by the driver. Okay, so actually in this discussion we have assumed that the driving system remains practically unaffected by the forced oscillation of the driven system. Actually the former only serves as a source of periodic force. This driver serves as a source of periodic force with negligible feedback of energy from the driven system. Okay, it means there is a flow of energy only in one direction. It means energy flows, we consider that energy flows only from the driver to the driven system. As I have marked symbolically in this figure, this flow of energy takes place from driver to the driven system. It means there is no flow of energy from the driven system to the driver. But how it is possible? Definitely there will be a flow of energy from the driven system to the driver, because both are mutually coupled. But in this case, we simply consider that the driven system extract energy from the driving system without any appreciable feedback of energy from the former to the latter. Okay, actually the transfer of energy is essentially a one-way process, and this is because either the coupling between the two is very weak, or the driving system has such a large amount of energy reservoir that the energy fed back into it is negligible. Okay, as I have told you that we consider that there is a flow of energy from the driver to the driven system, but in practice there may be a flow of energy from the driven system to the driver. Then how we can say that this energy flow takes place only from the driver to the driven system? Actually this can be possible in two situations, or this can be assumed in two situations. In first situation, you may assume that the coupling between the driver and the driven system is very weak. This coupling is very weak, and so that the driven system does not provide energy to the driver. Or it is also possible that the energy content or the energy reservoir of this driver is very high, very large. And so if there is some energy provided by the driven system to the driver, that amount of energy will be negligible in comparison to the energy already contained in the driver. So we simply say that this driver remains completely unaffected from the driven system. It means in this case, driver affects the driven system, but driven system does not affect the driver. So both are treated individually, both are independent from one another. Okay. Only there is the source, that is the driver, provides the necessary harmonic force or necessary energy for the free oscillation of the driven system. Okay. So I have mentioned it here. You can see the driving system, that is the driver, thus remains practically unaffected by the forced oscillation of the driven system. Okay. Driven system. Okay. The driving system only serves as the supplier of periodic force. Okay. These things we have assumed or we have learnt earlier. But when you talk about the actual practical situation, or when you talk about the coupled oscillations, what actually happens in this case? So in this series of lectures now, we shall analyze the oscillations of the coupled system, in which we cannot neglect the feedback energy from the driven system to the driver. You can't neglect. Okay. And it will happen only when the coupling will be tight, not loose, not weak. In that condition, there will be certainly an energy flow from the driven system to the driver. Okay. So I have mentioned here, you can see that in this case we cannot neglect the feedback energy from the driven system to the driver. The coupling is tight, okay, in this case, and these systems are said to have 2 degrees of freedom. This system has not 1 degree of freedom, but this system will have 2 degrees of freedom. Okay. Actually, you will see when we will discuss the actual problem that there are exactly 2 variables in terms of which there are exactly 2 variables. 2 variables in terms of which motion can be completely specified. And since such a motion can be specified or discussed in terms of 2 independent variables, so we simply say that the coupled oscillations has 2 degrees of freedom. Okay. Now we will see for example some of the 2 coupled oscillating system, as you can see in this figure. See here. I have shown here that in this figure A, there are 2 simple pendulums with their bobs attached to each other by means of a spring. As you can see, this is the bob of pendulum number 1, this is bob of the pendulum number 2, and these 2 bobs are connected to each other by this spring. Let us say of a spring constant K. So this is just a 2 coupled pendulums. Okay. And this is an ideal example of the 2 coupled oscillators. Okay. Similarly, in this figure B, you can see there are 2 masses. Say this is mass number 1 and this is mass number 2, and these 2 masses are connected by a spring, let us say of a spring constant K. And apart from that, you can see that these 2 masses are attached to each other by 3 springs. This middle spring actually provides the coupling, and these springs, this spring and this spring, are also needed for such 2 coupled masses. Okay. And in the third example, I have shown two LC circuits. You can see this is one of the LC circuit and this is the another LC circuit. And both are magnetically coupled to one another. Okay. Actually, all these three examples we will discuss in very detail in our forthcoming lectures. I am just introducing here you what is this coupled oscillations. Actually, in this case, the systems are said to have 2 degrees of freedom, not 1 degree of freedom. As you have seen earlier, that in case of a simple pendulum, oscillation of a simple pendulum, or oscillation of a spring mass system, or a single LC circuit, we need only one variable to deal with the motion of the system. And so those systems had actually 1 degree of freedom. But whenever you will discuss the problem which I have mentioned here, the problem of 2 coupled pendulums, or the problem of 2 coupled masses, or the problem of 2 coupled LC circuits, then actually we will see later that we need 2 variables to specify the oscillation or motion of such a system. And since we need 2 variables for dealing with such a problem, so we say that such systems have 2 degrees of freedom. Okay. Actually, when the moving parts of such a system oscillate in one plane, say the plane of paper, there are exactly 2 variables in terms of which the motion can be completely specified. For example, in case of this 2 coupled pendulums or 2 coupled masses, what are the 2 variables in terms of which the motion of 2 coupled pendulums and 2 coupled masses will be dealt? Actually, in the first 2 examples, that is the example of 2 coupled pendulums or 2 coupled masses, you will see later on the 2 variables in terms of which their motion will be described are actually the displacement of the 2 bobs, displacement of the bob number 1 and bob number 2, and or in case of 2 coupled masses, this is again the displacement of these 2 masses 1 and 2, which we need to deal with the oscillation. So these 2 systems has 2 degree of freedom. Similarly, in case of these 2 coupled LC circuits, the 2 variables are the charges on the capacitors, that is, you can take the charge on this capacitor or charge on this capacitor, let us say Q1 and Q2 minus Q2. Okay. You can take the charges on 2 capacitors as a variable for dealing with this oscillation. Or we can also take the current flowing in these 2 circuits. Let us say that I1 is the current flowing in the first circuit and I2 is the current flowing in the second circuit. So instead of the charges on the capacitor, we can also take the electric current flowing through the inductors in these 2 circuits as variables in terms of which this oscillation can be dealt. So from these 3 examples, it is clear that when we talk about the 2 coupled oscillators, in those examples, definitely the degree of freedom will be 2, because we will need 2 independent variables for dealing with the motion. Okay. Actually, in these examples, the 2 oscillators are coupled together so tightly that we neglect the feedback of energy from the driven oscillator to the driver. In fact, we can no longer distinguish between the driven oscillator from the one that provides the driving force. And we cannot label one as a driver and the other as a driven. So both the oscillators have now been treated on an equal footing. Okay. Actually, in physics, we come across a variety of coupled systems that can oscillate. In fact, oscillators rarely exist in complete isolation, which we have learned earlier that was actually ideal situation. In practice, oscillators are definitely coupled. Okay. A very important example of coupled oscillations we will discuss in next chapter in very detail, and that is the example of vibration of a string. We will deal with the problem of vibration of a string in our forthcoming lecture in very detail. Actually, when you talk about a string, you know that a string consists of a very large number of particles coupled to one another. Okay? Each and every particle of a string are coupled to one another. They are connected to one another by some elastic force. Okay? And this string is capable to vibrate in different modes in different ways. Actually, if this n represents the number of modes or number of ways in which an string vibrates, then there will be n frequencies, and this n may have any value 1, 2, 3, and so on. This may be a very large number. So in case of a free oscillator, there was only one characteristic frequency of oscillation. In case of two coupled oscillators, there will be two frequencies of vibration. But when you talk about vibration of a string, in such example, there is unlimited number of frequencies, okay, which are actually called fundamental frequencies and overtones. We will discuss it later on. Okay. So if you talk about the vibration of a string, as I have told you that this string consists of a large number of particles coupled together, and each particle of the string behaves like an oscillator. Okay. And this string is capable of vibrating in many different ways or many different modes. Okay. And each mode has its own characteristic frequency. So I have told you that if n is the number of modes or number of ways of vibrating of a string, then there will be n characteristic frequency of the vibration of a string. So how we can account for these numerous modes and calculate the frequency of each mode? This question will be answered when we will discuss the vibration of a string in our next chapter. Okay. Actually, the clue lies in the fact that a string or any extended object can be regarded as an extended array of large number of simple oscillators coupled together. Okay. Another very important example of a coupled system is our solid. When you discuss the vibration of solid in the course of your solid state physics or thermal physics, definitely you have studied Device theory of heat capacity, and you have seen that a solid is treated as a composition of a very large number of atoms. Okay. And each atom behaves as an oscillator, vibrating about an equilibrium position. Okay. the motion of each atom affects its neighbors. Okay. In Einstein's theory, it was assumed that the vibration of an atom remains unaffected from the neighbors, which was a fault of Einstein's theory, drawback of Einstein's theory. Debye has actually removed this drawback, and he assumed that in case of solid, the atoms are so tightly bonded that we cannot neglect the coupling of atoms, and so the vibration of each atom is affected by the its neighboring atoms. Okay. Thus, all the atoms in a solid are coupled together, you can say, and we have therefore to answer the following specific questions. What are those questions? The first one is, what is the effect of coupling on the behavior of individual oscillators? To answer this question, we shall begin by discussing in some detail the behavior of system with just two coupled oscillators. You will see later on. Okay? And finally, we will develop on an analytical method for solving such problems. Okay? And after that, we will use the method to discuss the problem of an arbitrary large but finite number of n oscillators. Okay? Actually, after dealing with the problem of this coupled oscillators, then in the next chapter, we will consider the case when the number of oscillators n tends to infinity. When n tends to infinity, the medium becomes continuous. Okay? Medium becomes continuous. And this n tending towards infinity just gives the idea of waves. So we simply say that when we will take n tending towards infinity, then we will enter into the domain of waves. So how important this concept of coupled oscillation is, you can imagine. Because first of all, in this chapter, we will limit our discussion only to the coupling of two oscillators. But in the next chapter, when we will start to deal with the problem of vibration of a string, then the problem will remain same. We will again discuss the problem of coupled oscillations. But in that case, the number of oscillators coupled together will be very large. In general, we say that there are n oscillators. Okay? And finally, in case of the problem of waves, you will find that the problem of waves is also the case of coupled oscillators. But in this case, the number of coupled oscillators will tend to infinity. So the idea from oscillation, how the idea from oscillation to wave is transformed, we will see. So this chapter is called Waves and Oscillation, because waves is just a limiting situation of the oscillation. When the number of coupled oscillators becomes infinitely large, then the problem of oscillation becomes the problem of waves. Okay? So the main fact of the problem of coupled oscillation is what? It is just the problem of exchange of energy, that in this case we cannot neglect, we cannot say that energy is provided by the driving system to the driven system only. But in this case, you have to consider that there is a mutual flow of energy. That is, energy also flows from the driven system to the driver. Okay? So this was just a brief introduction regarding this coupled oscillations, and after this introduction, we will actually start our real concept of the coupled oscillations, and we will develop the concept of normal modes and normal coordinates, which is a very important idea, very important concept. So watch the video seriously, and definitely you have to watch all the videos in sequence so that the idea of this coupled oscillations will be crystal clear to you. Okay. Thank you very much.